Hello everybody, I'm going to introduce Peter Sobot. He's going to tell you about working with audio in Python with his repository pedalboard. Let's give him a warm welcome.
Thank you. All right. Thank you, PyCon. My name is Peter Sobot, and I'm here today to talk to you about how to work with audio in Python. So first off, why am I up here talking at you? Well, by day I work as a staff machine learning engineer at Spotify in our audio intelligence lab. It's a research team that works on building machine learning models to analyze and understand music. Now we build features that go into the Spotify app, but we also open source a lot of our work, and I'll be talking about a lot of that today in case you want to play with it. Some of the stuff you might have seen before, we have open APIs that you can use to access data about music on Spotify. We use machine learning and build a lot of this in Python, and we figure out how to tell you the key, the tempo, the danceability, the energy, the beats, the bars, all sorts of information about music that you might be listening to. But that's just an API. We've also open sourced many machine learning models before, which you might be able to play with and build stuff on top of. So we've open sourced models like this one here called Basic Pitch, which is an audio to MIDI converter. It allows you to take music as input and then get a listing of the notes that were played in that audio. It's totally open source on GitHub. You can run this in Python, you can run this in your browser, run it wherever. And we also open sourced a lot of more foundational infrastructure work. For instance, this library here called Pedalboard, which I'll be talking about later on in the talk. It's, in my opinion, one of the best ways to work with audio in Python, but that's the whole point of the talk, so I can't spoil it. Let me start slowly here. So this is PyCon. This is not an audio conference, so I'm going to start by telling you all about how audio works in the first place. I assume you know what Python is, but working with audio might be new to you, so we'll go through a quick primer there. Then we'll talk about some gotchas. Then we'll talk about some reading and editing audio in Python, how we can use Python's built-in syntax and built-in tooling to read in audio files and edit them. Then we'll move on to different problems you might find working with audio in Python, different gotchas, different weird things you might not expect because audio is shaped a little bit differently. And then finally, we'll talk about Pedalboard itself and show off some cool features and ways that you can use it to make your audio code a lot easier to use and do a lot of really, really cool stuff without having to write a bunch of complicated math. And before I actually get into the content, this is an interactive talk in a way. This is super experimental. Apologies if this doesn't work. But I've built a little in-browser demo that you can play with here. If you scan this QR code or go to that link on the screen, spotify.github.io/pedalboard/demo, then you'll be able to play with Pedalboard in your browser using Pyodide and Emscripten and WebAssembly and all those cool technologies. You can actually even load audio files by dropping them into the browser, and you can play them back just by executing code in your browser there. And if somebody were to make sound during my talk because they're playing with this REPL, I would be overjoyed. I would be very, very proud. So please have fun with it. It might not work, but if it doesn't work, just refresh and try again. Okay, so let's start from the very top here. How does digital audio work? To answer this question, we're going to need to go even further back and understand how does sound work? What is sound to begin with? Well, if you're not familiar with the physics of it, which I don't expect you would be, sound is really just pressure traveling through the air. That's how you're hearing my voice right now. My voice is vibrating the air in front of me, going into this microphone. That's coming out the speakers in this room, and they're just pushing vibrations through the air. It's going back and forth, and that's hitting your ear and causing sound to occur, as it were. Digital audio is really just a digital version of this sound. So just like everything else in computers, if we want to take a physical phenomenon and get it into a computer, we just have to measure it. So I'm going to measure some sound here. I'm going to have a graph on the screen here that has time in seconds on the x-axis and then has pressure on the y-axis. And I'll play a little clip and we'll see samples of the pressure as the clip plays. So watch as this happens here. So that was a little saxophone clip, and you could hear that with your ears, but we can also see that visually here. I took samples of the pressure coming out of my speakers here as that was playing, and we can see there's some sort of graph on the screen. It doesn't make much sense to start with, and that's actually because we only took one sample every 0.4 seconds here. If we take the reciprocal of that, that's called a sampling rate, and this sample rate or sample frequency is very important for digital audio. The faster that you sample, the higher quality audio that you get, or rather the more details you're able to capture, and the higher frequencies you're able to capture in that as well. I captured way too few frequencies here for us to actually reproduce that sound properly. But other interesting things about digital audio here, the bottom of this graph is actually not quietness or silence. Silence is in the middle of this graph. And that's because any sort of audio can move back and forth, right? Pressure is that wave moving back and forth in the air. So silence is at the middle of this graph, and then maximum loudness is both at the top and bottom of this graph, at plus 1.0 and minus 1.0. Our ears don't really tell the difference between a wave coming towards us and going away from us, but when you measure, it actually makes a huge difference here. And then we can just take each of these points and measure the distance from the 0 point here. So we can measure that this point is 60% amplitude in the positive direction, or 0.60 if measured as a floating point number. This point here is 90% amplitude, but in the negative direction. That's negative 0.90, and so on. So all of this together gives us a list of numbers that we can use to represent this audio. And we can try to connect these points. We actually try to make a little graph here. This doesn't really do anything important for us, but it tries to show that we're capturing a larger waveform here. But again, if we want to reproduce this audio, we're going to have to do something much more high fidelity. So let's record this again, but instead of sampling at 2.5 hertz, let's sample at 44,100 hertz, which is the common sample rate used in most digital audio. So I'll do that again, and we'll see what this looks like this time. And there we go. Now we have a waveform, as it's called. It's much, much more detailed. In fact, it's so detailed we can't see the individual points here. All we can see is the overall shape and the loudness of the sound as it changes over time. You can even kind of make out the notes that the saxophone played there because there are certain notes that are louder than others. But let's zoom in here. We're looking at a multi-second scale here. Let's look at the millisecond scale instead. I'm going to zoom this waveform all the way in. And we see that the blobs start to dissolve, and now we just see the individual waves, the oscillations in the air that we heard there. We can do really cool stuff at this level too. We can actually measure the distance between these waves, or distance between these peaks here, and get interesting information about the music or the audio itself. So the distance between these peaks here is 5.7142 milliseconds, sorry. And if I take the reciprocal of that and then look that up in some sort of table, I can find the note that the saxophone played. It was actually an F, a concert F. And we can find that just by looking at the waves that came in off the microphone and trying to get all that information there. But I want to go even deeper here. I don't want to just look at this pretty graph. I want to see the individual samples. I want to see the most basic representation of this audio possible. And when we get down to the microsecond level, then we start to see the individual samples. These are the actual numbers that were captured by the microphone or by the sound card, by the digital audio converter, or digital analog converter. And this is essentially all that digital audio is. It's just a series of numbers. It's just a stream of numbers. There's nothing magic about it. If you capture these numbers and you capture the sample rate that they were captured at and store that alongside it, you have enough information to reproduce this exact signal. So let's save this. Let's take these numbers and try to put them on disk and use them in a way that we can then play them back later or load them or process them in some way. If I were to save this data on disk as it is now, this is what's called uncompressed floating point representation of the audio. This is essentially 32-bit or 64-bit floating point numbers. And if we just store those on disk, that's 21 megabytes per minute of audio per channel, which is pretty heavy. It's pretty expensive. That's a lot of data. We wouldn't want to use this for, let's say, streaming audio over the network or for storing your entire music library on your device or something like that. So instead, very smart people came up with compression algorithms. Compressed floating point representations are very common nowadays, like MP3 and OGG, even FLAC, things like that. And these get the data rate down much lower by throwing away parts of the audio that you can't really hear, parts that are hidden behind other parts of the audio or higher frequencies that our ears aren't sensitive to. And you might notice on the screen here that the actual byte contents no longer represent the floating point values that we've got. So if we want to decode this audio and work with it, we're going to need to use some sort of libraries. And that's where we need to look at the ecosystem of all the stuff that's in Python available for working with audio. So let's start by reading and editing audio in Python by going to the standard library. Right? Python is batteries included. There should be something in there for reading audio. And indeed there is. For a very long time, there's been a package called the WAV package. It loads WAV files. It allows you to read WAV files. It allows you to manipulate the data within. And let's take a look at what that interface looks like. Here we've got wave.open. We'll open some audio.wav. We'll get the frame rate from that WAV file. We'll get the number of channels in that WAV file. We'll get the number of frames overall, which is actually not related to the frame rate before. That's kind of weird. That's not an amazing API. And we'll get the sample width, which is 2, which kind of oddly enough means that we have 16 bits per sample here. So you need to know a little bit about how WAV works if you want to use this API. And then you can read individual frames of audio out of this WAV file, but then you end up getting byte strings. So here I've got 00 and then hex 18, hex 15. This is a really low-level API. It technically works, but you have to do a lot of additional work on top of it if you want to just get information that you can intelligibly deal with. So let's do a little bit of that work ourselves in Python and see what that looks like. Let's import WAV, and then let's import the array package, which is also built into Python standard library. Let's open a WAV file, And then let's call array.array. Let's create an array with signed 16-bit integers in it, which is the same data format that Wave uses. Let's read 10 frames from that Wave file into this array. And then now we can see that this array has parsed these values as numbers. So we have integer values here, signed 16-bit. And if we want to convert those to floating point, then we can use a list comprehension here to do x over the maximum signed floating point value, or sorry, signed 16-bit integer value, and then we get our floats. So technically we can read a WAV file and get intelligible data out of this, but it's kind of a pain. So I wouldn't recommend that you use this. Also, this only works for WAV files. Also, this only has many caveats and limitations on it. So instead, I'd suggest that you use a library. I happen to like a particular library. It's the one that I maintain. It's called Pedalboard, and you can do from pedalboard.io, import audio file here. Looks just like that. You can use audio file just like the open function in Python to open a file, and you get a file handle just like you would expect. So it's very natural, behaves just like any other file that you would expect to use. You can look at properties on that audio file. You do f.sample rate here, and you get 44100, which is the sample rate of the file. You can do f.num channels to get the number of channels. It all just kind of makes sense. And then if you want to read data out of that file, if you want to decode this MP3 on the fly, well, you just call f.read. In this case, you get a multidimensional array of shape 2, 3. That's 2 channels by 3 samples that you asked for per channel. If you're not familiar with multidimensional arrays, that's okay. Just think of them as nested arrays, arrays of arrays, essentially, where all of the inner arrays have the same shape. And here, because we have a left and a right channel in this MP3 file, the first 3 values are the left channel, and the second 3 values are the right channel. So multidimensional arrays are pretty useful here, but they don't take that much getting used to. Let's see what else we can do here by opening up an audio file and then slicing around the data within it. Let's open up this file and read the entire thing into memory. So I'll do f.read f.frames, and this gives us an array of shape 2, which is the number of channels again, and then 1.3 million samples, which is roughly 30 seconds of audio at this sample rate. So it seems like a lot of data, but it's really not that much because we have 44,000 samples coming per second. If we want to slice this up by channel, that's actually really easy. This is a multidimensional array, so we just have to do audio at 0 and then audio at 1 if we want to get the left or right channel respectively. And if we want to slice this up in time, well, we just slice on the second dimension. So we can pass an empty slice to the first argument of our slice operator here, and then we can do :100, for instance, to get the first 100 samples. Or if we want to multiply by the sample rate, that works too. We can do :f.sample rate times 10, and that'll give us the first 10 seconds of this chunk of audio that we've read. We can do more complicated things as you would expect, like -f.sample rate times 10 to get the last 10 seconds and so on. We can also seek around in this file though. So because this is an open file handle, it behaves just like you would expect. We can seek to any point in the file by indexing by sample index. So here I can skip to the 10-second mark by seeking to f.sample rate times 10. Or we can we can then read 10 seconds from that 10-second point by doing f.read f.sample rate times 10. And again, it behaves just like an open file handle, so it should be pretty familiar to those who've used that in Python. But okay, that lets us load data from an audio file and then parse it and then decode it and then do all this kind of slicing. What happens if we want to try to edit it? Well, that's actually pretty easy as well. Let's undo a lot of this stuff and let's start to edit by changing this audio file by adding a delay effect or an echo effect. Let's see what that sounds like. So I'm going to take this audio, I'm going to take just the left channel just for simplicity's sake here. And if we're going to add an echo or a delay effect, I'm going to define some parameters up front that tell us what that echo should do. So I'll set my delay in seconds to 0.2 or 1/5 of a second. I'll convert that to samples just so it's more easy to do the math with. And then I'll set a volume for how loud I want that echo to be. And it'll be 75% of the original volume of the audio. Then I'm going to do some, and this is scary, digital signal processing code in Python. Don't worry, it's actually only 2 lines. I'm going to iterate through every single sample in this buffer, and then I'm going to make a copy of each sample and put it forward in time and multiply that copy by the volume that I want. So if that didn't make sense, don't worry about it, because one of the fun things you can do with audio code is just listen to it to see the effect that it's had. So let's do that. Let me play you what I'm going to put into this code, and then we'll hear what comes out the other side in 1 second. So here's the input to this function. And then once we've added this delay on top, and hopefully that was audible, you could actually understand that there was a difference there. What we've done in these 6, 7 lines of Python code is really quite simple, and yet it's had a noticeable effect on the audio coming out here. So it's that simple to make simple effects like that. Let's try one more very simple effect in Python. Let's try to change the quality of the sound rather than adding some more rhythmic changes to it. I'm going to read in a file here called coolguitar.wave. It is what it sounds like. It's a cool guitar sample. And I'm going to make it distorted. I'm going to add some gain to it. I'm going to define a parameter for volume to make it a little quieter afterwards because I don't want it to blow the speakers out. And then I'm going to do a for loop again here. I'm going to loop through every sample in the buffer, and I'm going to apply a function from the math package in Python called tanh, the hyperbolic tangent function. You don't need to worry about what this does. Just know that it adds a pleasing distortion effect to the sound, essentially. And here's the effect that that has. If I pass in this signal here, then I get this signal out. Much more loud and distorted and amplified and all that good stuff. It sounds more metal, more rock, whatever you want to call it. And all we had to do was run these 6 lines of code here. So not too complicated to play around with audio in Python directly. But if that's how you can play with audio pretty easily in Python, where are the pitfalls? Where are you going to run into trouble? Well, that's an important topic I want to cover briefly here. Let's talk about a couple problems you'll see working with audio data in general and then also in Python. So let's say we want to build a little application that makes a certain audio file louder. Maybe it's a web service, maybe we're providing this to someone else, maybe it's on the internet. And we load in whatever audio file our users give to us. We load the entire audio file into memory with Pedalboard here, and we make it louder just by multiplying every sample by 2. Don't do this, by the way, but it's just an example. And then we write the resulting file back out to an MP3. You can actually do that in Pedalboard just like this. You open past the W flag just like you would with the open call. And then you call o.write to write that, encode that MP3, and you're done. And this works for a while. Your users are happy. And then you wake up and you're getting paged because this has crashed. This is not working in production. Your entire server has gone down. Your Python process has died. And that's for a very interesting reason. I would ask if anybody sees the reason, but I want to show something first here. I tested this just with myfavoritesong.mp3. And myfavoritesong.mp3 is 3 minutes, 22 seconds long. It's pretty short. It's 5 megabytes on disk, and because it's using MP3 compression, when you decompress that and put that into memory, well, then it's using 68 megabytes in memory. So MP3 compression is fairly efficient, but like not extremely efficient. This is 14 times compression here. It's quite a bit. And then this is a web service. Maybe we're providing this to other people, and they start uploading random files to us. Maybe one person uploads cool podcast episode.mp3, which is actually 60 minutes long, which, you know, that's a lot more data. But podcast episodes are actually, they don't take as much compression, or they don't have as much data in them as music does, so they compress well. So this is 28.8 megabytes on disk. Not that bad, you know, a good compression ratio. But when you decompress this takes up 1.2 gigabytes in memory. So that's quite a bit more, and you wouldn't really know this until after you've already done the decompression because the original file size is pretty small. This is a 42x compression ratio. And then you find out why you got paged in the first place, and that's because someone uploaded something called whoopsallsilence.og, and whoopsallsilence.og is 12 hours of just zeros, just silence, no audio at all. OGG is actually a very, very good compression format, and so that compresses down to 3.9 megabytes on disk. So nobody thought that this was a lot of data, right? This is just a tiny file. But then you decompress it, and it's 14.2 gigabytes in memory, and that's a compression ratio of 7,772. So because there's this discrepancy between the file size of a compressed audio file and the actual audio content within, you always, always, always should treat these files as if they could be any length. And luckily, that's very easy to do in Python. Let me show you how. So for instance, we can open up our input file that we want to process here, just like we did before. But let's also open our output file on the second line. Yes, I know that you can nest the context managers. Henrik, don't say anything. Let's loop through the input file. Let's kind of scroll through it in chunks here. While there is more to read from this original file, let's read a single chunk of 500,000 samples from the input file. Let's make that single chunk louder, and then let's write that chunk to the output file. So this is only 2 or 3 lines more than we had before, but now this is infinitely scalable. There's no reason this will crash because we're only ever processing 4 megabytes of audio at a time because we've bounded our chunk size. It's 500,000 samples always. And this is a good way to avoid crashes in your real production audio applications. So if there's one thing you take away from this talk, it's that I think you should think of audio as a stream. Audio can go on for as long as you want it to. There are real-time audio situations where audio literally is a stream. There is no end to the stream. And if you architect your software in that way, you're not going to crash nearly as often. Thank you, Lukash. Somebody actually used the demo. I love it. Okay. One other problem working with audio in Python. Let's go back to my example of coolguitar.wave here, where we add distortion to an audio signal. And here, I was doing some digital signal processing in these two lines of Python. I was applying the tanh function. If you've worked with Python for any length of time, you probably know where this is going already. But I profiled this, and I found that it takes 8 seconds per minute of audio to process. Another way to say that is it's 7.5 times faster than just playing the audio back in real time. And that's okay. It's faster than real time, so we could run this without delaying playback or something like that. But it could be faster, right? This is just doing a lot of math operations. Why is it so slow? And of course, if you pull in NumPy, the very common library for audio, or sorry, for just numerical processing in Python, you'll find that the same exact operation takes 23 milliseconds per minute of audio, or is 2,541 times faster than real time. If we divide these two, this should come as no surprise, but it's 338 times faster to use NumPy operations instead of for loops for doing this kind of audio processing. And this is because Python itself is not really optimized for doing a ton of numerical computation. This is something that I don't need to tell you. You've probably heard this in a million other places. But for audio, pure Python is slow. You should always avoid looping through an entire audio buffer or processing sample by sample. And if possible, you should always pass that audio to a lower level library that's able to do all of that hard DSP calculation in C or C++ or in Rust. There are plenty such libraries, but you might have heard of this one. Thank you, Chris. You might have heard of this one called Pedalboard, which is in the name of my talk and also the library that I help maintain. So a quick aside here before I keep going though, it's called Pedalboard. Do we have anybody in the room who plays electric guitar or electric bass? We have a lot of people. That's excellent. Okay, so you probably all know, or many of you know about what these are. Is that right? Good, okay. So for those who don't play electric guitar or bass, this is called a pedalboard. It is a device essentially that guitarists and bassists use to change the sound of their instruments. They'll plug their instrument into one side, they'll plug their amp to the other side, and they have all these choices of how to affect the sound of their instrument. You can turn these pedals on and off, you can adjust the settings and so on. And the library pedalboard that I'm talking about today is essentially this, but in Python. You're able to do all of these effects and many, many more, and many other audio-related operations in Python, and it just happened to be available on PyPI, so why not call the package pedalboard? So let's see what that looks like. Let's try to apply some audio effects to the audio that we've already been playing with, but by loading them from pedalboard. So I'm going to load up coolguitar.wave here. Let's read the entire thing into memory, even though I literally just told you not to do that. I'm doing it just because it fits on the slide. And then let's do from pedalboard import reverb, capital R reverb. We're going to import the reverb class here. We're going to use that reverb class to create an instance of the reverb class. So we're creating a reverb plugin essentially, or a reverb pedal if you'd like. And we're going to set the initial room size to 75%, just one of the many parameters that it has on it. And then we're going to apply this reverb pedal to our audio by just calling it like a function. So small r reverb will pass in audio and f.samplerate, and it'll generate us the affected audio here. And here's what that sounds like. Here's what I'm going to pass into it. And then here's what comes out of the other end. So I know this is a big conference hall, but hopefully you could hear the difference there. We added even more boominess, even more reverberation to that sound, and all we had to do was import the reverb plugin here. But it's not very common that you just want to add a single plugin. You often want to add multiple plugins in series or in parallel or so on, and Pedalboard has all of that built in as well. So let's create a Pedalboard object itself, which is just a list of plugins that are going to run in series, and let's pass in a distortion plugin, followed by a followed by a delay plugin, followed by a reverb plugin. We actually already know how to build the distortion and delay plugins in Python because that's what we did on the previous slides, but now we're just going to put all this together and use the underlying C++ code to do this a lot faster. So I'm going to apply this entire pedalboard here, again, just by calling it as a function, and I'll pass this audio in. And then here's the output of the entire thing. So hopefully you can tell that difference. That's now a huge wash of sound because we've added distortion followed by delay followed by reverb. It's a very professional sounding clip. And again, all we had to do was import the existing plugins here. So actually Pedalboard ships with a ton of plugins. We've got all of these here, bit crushing, chorus, clipping, compressor. The list just goes on and on and on. But that's not enough because if you've ever worked with audio software, you've probably seen that there are third-party plugins that people really like. They like to load what are called VSTs or audio units into their audio software. And Pedalboard can do that too. So let's do that right here. Let's do from Pedalboard import load plugin. We'll load up our cleanguitar.wave again. And then we'll call load plugin to load a third-party virtual studio technology plugin here. VST3 is the suffix there. And these are actually GUI applications, so you can call plugin.showEditor, and that'll pop open the GUI window for you. And you can play around with this, you can use your mouse and keyboard and do whatever you need to in that interface. But if you don't want to do that, you can also access all those plugins parameters on in the Python code directly. You can do plugin.gain to get the value of the gain parameter, you can set the gain to whatever you want, and then again, to invoke this, we're just going to call it like a function again. So I'll do with effects here, and let's pass this in. And now I didn't write any DSP code for this, but I get to use what's in this plugin to make it sound like this. So this is something that you would be able to use in your digital audio workstation, in Ableton, GarageBand, Logic Pro, Cubase, whatever have you, and now you can use it in Python as well. There's a couple other things you can also do here. We can also load instrument plugins too. So not just effect plugins, but you can load plugins that take MIDI as input. I'm not going to talk too much about this, but I'm going to load this plugin here, which is a MIDI synthesizer that emulates old video game consoles. I think this is emulating the Nintendo Entertainment System. And I'll pass in a list of notes here, and then we'll convert those notes into MIDI messages, and then we'll pass those MIDI messages into the plugin itself. And I wish this would type faster. But with all of this, we'll save this to a file, and with these 10-ish lines of code, we're able to render these notes. And with that, you've got the building blocks to put together your own little digital audio workstation in Python directly. So I've only got a couple minutes left. I'm going to breeze through a couple things that you might be interested in if you already live in this world of audio. I'll do a bonus round here of advanced pedalboard topics. So I'll start with resampling. If anybody's ever worked with audio, you've probably had to take audio at one sample rate and convert it to another sample rate. Pedalboard has that built in. If you're reading in audio and want to convert it, all you need to do is add .resampled to the end of your audio file call, and it'll automatically resample on the fly. This is constant time, constant memory, super cool. I can talk about this at length if you want to talk afterwards about this. This works really well. But you can also do things like time stretching. So with the pedalboard time stretch function here, you can take an existing audio file and make it faster or slower. So here's that same clip from before, but twice as fast. I can't play guitar that fast. That was entirely the code. But there's a whole bunch of other stuff you can do too. If you need to encode audio into any format that you want, you can use audiofile.encode. Just pass it in an audio buffer and the format you want to encode to, MP3, FLAC, OGG, many other formats, and it's one line of code there. Or if you want to pass that into a file like object, that's supported as well. You can read from network streams, you can decode on the fly, you can do all this kind of stuff that you would expect from any Python library that integrates with the Python ecosystem. You can also stream audio to your speakers. This is not part of the talk directly here. I'm not actually playing the live audio from Python, but you can use the audio stream function, find this in the documentation, to play audio directly to your speakers, or to consume audio from your speaker or from your microphone and then affect it in some way and play it back to your speakers in real time. So all of this is something that's happening live as you're using Pedalboard. Or you can record audio directly using AudioStream here, just like this. You can open up an audio stream and then do stream.read on it to read a certain number of samples, and then you can process those samples however you want. You can analyze them, you can save them to a file, you can do whatever you need to do. So I barely scratched the surface there. There's a lot more in Pedalboard. You can find a lot more of that in our documentation on GitHub. Find the package itself at github.com/Spotify/pedalboard. Find the docs linked there or at spotify.github.io/pedalboard. And thank you so much for having me. Find me after this talk for stickers of this beautiful logo, and be sure to go to Lukash's talk tomorrow at 1:30 p.m. in this very same room, also about audio. Thanks so much, PyCon. And I think I do have a couple minutes for questions. Is that right? Yes, okay. If you have questions, there are mics in the middle of the room.
So quick question. So what kind of hardware do you require to do the transformations you just demoed? Do we require high-end hardware, or is it a relatively cheap operation?
Right, so for hardware, all of this is actually surprisingly cheap. You don't need any sort of advanced hardware to do any of this because most of the actual logic is happening in C++, and all of this audio software has been heavily optimized over the past 30 years where people have been writing it. So I think people have run this on Raspberry Pis just fine, and yeah, you can do lots of different effects at the same time. Of course, if you import third-party effects, then they might be a little heavier or require more computation. But yeah, runs on a Pi, no problem. Paul.
Yeah, so I saw that you can load arbitrary samples from within like an MP3 file, right? Can you jump around? And then the second question is, what happens if you jump in the middle of a frame?
Good questions, yes. So you can seek to basically any point that you want to in an entire MP3 file. Apologies, I'll actually pull that code back up here. But the open file handle allows you to do whatever you need to there. I think it's on this slide here. Yeah, if you seek to the middle of a frame or the middle of a file, it doesn't really matter. We index in samples, and we'll move to the start of that frame, decode the entire thing, and then move forward to find the exact point that you wanted to get to. So it behaves just like a stream, as if you had decoded the entire thing, and the results are identical. Yeah. Next question.
Yeah, do you have any support for dithering or noise shaping
Good question.
during your conversions?
There is no dithering or noise shaping support right now because everything in Pedalboard currently uses float32 as its internal format. But that would be a welcome pull request for sure. We don't do any integer sample stuff at the moment. Yeah.
Hey, great talk. Thanks for it. So I know there are Python libraries for talking MIDI, like live direct to a device, right? Would it be possible to like build a physical pedal with like a Raspberry Pi inside of it running this software and then like talk MIDI to another device, like a foot switch or something like that, or an analog like wah pedal, and then affect the effects running in Pedalboard?
It should definitely be possible. I have not tried it myself. As I mentioned before, somebody has been running Pedalboard on a Raspberry Pi with no problems, and connecting that up so that you're reading the GPIO and then passing it to the appropriate place is just a matter of writing the appropriate Python code. So definitely possible. Yeah.
Very cool.
Awesome. I think that's all the questions. I have stickers if you want to stick around, but thanks so much for coming.